And now we have a talk by Joshua Gancher on a core calculus for equational proofs of cryptographic protocols. Take it away.
Thank you. So this work is part of a long line of research on mechanizing the proofs of cryptographic protocols. And while there continue to be a lot of success stories in this space, one of the biggest open problems here is the best way to formalize observational equivalences of interactive distributed protocols. Observational equivalence is really important for crypto because it's used to encode Universal Composability, or UC, which serves as a common framework for formalizing arbitrary crypto protocols. In UC, you model the protocol as an interaction with a number of parties, each of which talks to an algorithm called the environment, which handles both the high-level I/O of the parties, as well as any possible actions taken by the attacker, such as controlling the untrusted network. To prove that this protocol is secure, we compare it to an idealization, shown here on the right, where each party instead talks to a trusted third party. Our protocol is then secure if no polynomial time probabilistic environment can distinguish the real protocol from the idealization. I'm adding a bunch of modeling details here, but the high-level point is that observational equivalence via UC is central to advanced crypto proofs, and because of this, it's often called the gold standard for cryptographic security. Unfortunately, current verification tools don't yet enable really easy proofs of observational equivalence. As you might guess, the default technique is bisimulation. Given a pair of real and ideal states, you come up with an invariant R that relates the two states, such that whenever the real protocol can take a step, the ideal protocol can take a matching step, and the two states are still related by R. And if you could show that they always stay related, you can use this relation R to guarantee that nobody can distinguish the real from the ideal protocol. Of course, the issue is finding this relation R. For large-scale protocols, these relations get exponentially more complex, particularly for protocols like secure multi-party computation, where the protocol is defined inductively over a computation circuit, and protocols between n parties. What makes things even worse is that cryptographic proofs usually don't consist of just one observational equivalence proof, but instead many chained together. You prove security through a bunch of intermediate hybrids. Since each hybrid proof is a different bisimulation proof, you now have n complicated relations to define over whole protocol states and not just one. So if bisimulation is not the answer, what is? Well, if you look at the hybrid protocol technique, which is basically present in a lot of crypto proofs in some way, you'll see that many crypto proofs are inherently equational. So why do we instead try to embrace the equational nature of these proofs? So what we have found is that there are two main barriers to equational reasoning in the present frameworks: the use of opaque transition systems and the presence of scheduling leaks. In prior work, protocols are defined using the actor model. As is usual in the actor model, each party is activated with a message in its mailbox, which can be from an arbitrary other person. The party itself is defined by an arbitrary stateful imperative program that determines its next state and output message to send to somebody else. While expressive, the problem is that assuming absolutely no structure on the parties also means that in general, you need to use the most general proof technique possible, bisimulation. The next issue is that parties in the actor model can do some unintuitive things which gets in the way of reasoning. For example, it's easy to express behaviors like, if I don't get a message from Alice within a certain amount of time, send a message to Bob. Put another way, all of the low-level non-deterministic scheduling decisions can leak into the messages that are sent by the parties, which significantly complicates the equational reasoning. This is really unfortunate because we have found that these kinds of unintuitive behaviors don't actually show up in most crypto proofs. So there must be a better way. Our new insight is to restrict our attention to confluent by default protocols. These are the protocols where the data being passed around is provably independent of low-level scheduling decisions. And instead of using opaque transition systems for the parties, we define protocols through a process calculus that gives us the structure that we need to do the equational proofs. And this brings us to IPDL. IPDL has two components. First, it has an extremely simple, novel core language for cryptographic protocols, which eliminates a lot of the boring low-level details and lets you focus on the crypto. Second, it comes prepackaged with an equational logic, which lets you carry out crypto proofs of distributed protocols as you always wanted to, without any explicit low-level bisimulation arguments. Finally, we mechanize the IPDL calculus and equational logic in Coq and carry out a wide range of case studies, including modular proofs of key exchange and secure multi-party computation. Due to our use of equational reasoning, our case studies are complex but small. All of them are less than 2,300 lines of code, and that's counting both the protocol's definition and its proof of security. To support easy equational proofs, IPDL uses a slightly different computational model than prior work. Instead of a traditional actor model of communicating sequential programs, IPDL represents both parties and whole crypto protocols using networks of probabilistic programs. An example network is shown here. We flip a coin and pass its value to an XOR function who gets its other argument from the external environment. The output of the network is then the output of the XOR. Networks in IPDL are expressed using write-once channels. Thus, this network only uses one input and produces only one output. Multiple sessions of the protocol could be encoded using families of write-once channels. The point is, using IPDL, we will show that this network is observationally equivalent to this other one on the right that ignores this input and just outputs the coin flip. While simple, this proof demonstrates the power of equational reasoning for security, since ignoring the input can be seen as a privacy property. And also, while this network is simple, it serves as a very flexible way to specify and reason about protocols. As an example, this network here can be seen as the code for the party Alice in a protocol. The network has two sets of interfaces given through external channels. The channels on the right are meant to communicate with the other party, while the channels on the bottom are meant for the environment, who observes the high-level I/O behavior of the protocol. We can then do the same for the other party, Bob. They then communicate through what's called in crypto a network functionality, which serves to deliver the messages between the two parties. The channels in red on the bottom here are the channels for the attacker to communicate with the network. We can use these channels, for example, to allow the attacker to view and modify the in-flight messages if your communication model is unauthenticated. Now, crucially, networks in IPDL are agnostic whether they represent single parties or entire protocols. Thus, it's easy to combine parties together by hooking up their IPDL networks to create a new, larger network. The ability to refactor protocols modularly drives all of our case studies. Additionally, the equational logic of IPDL allows us to simplify arbitrary IPDL networks. By combining Alice and the network together first, we're able to then discover new protocol simplifications that aren't present when we consider each party separately. Our ability to perform protocol normalization steps like this allows us to get rid of irrelevant details in protocols and often discover new proof strategies interactively. Now let's go back to our flip and XOR example. We encode this protocol in IPDL by first assigning each atomic box here a reaction, which is a little monadic program that can read from other channels and perform probabilistic operations. To write our protocol, we'll need to give names for the channels for this protocol. C for the coin flip, and INO for the input and the output. The reaction for flip here is just a single line, which executes a primitive coin flip operation. The reaction for XOR is more interesting. We read from C, read from I, and then output the XOR of the two values. We encode this network in IPDL as the protocol definition P here on the right, which has two free channel variables INO for the input and the output. We first create a local channel, C, to hold the output of this flip reaction. We don't show it here, but local channels are annotated with a type for the data that they hold. Next, we have channel assignment, which assigns each reaction an output channel. Finally, we have parallel composition, which allows two IPDL protocols to interleave and interact concurrently. And that's it. The core grammar of IPDL is given by just these three combinators. I won't go into detail, but IPDL protocols are strongly typed. This protocol P has type I to O, which means that I is an input, while O is an external output. IPDL's type system ensures that every channel is assigned at most one reaction. The type annotation 1 on the channels I and O here refer to the length of bit strings attached to the channel. For soundness against polynomial time cryptographic machines, each channel is typed with a length of concrete bit strings that they carry. Now let's turn to the equational logic. IPDL's equational logic is split up into two halves. There's an exact equational logic and an approximate one. The exact one is where you spend actually most of your time and involves simplifying, rewriting, and refactoring protocols. The approximate one is how you state and prove cryptographic hardness assumptions, like the security of encryption, hardness of one-way functions, and other crypto stuff. Intuitively, if P is approximately equivalent to Q, then no efficient adversary can distinguish interacting with P from interacting with Q. Our formalization uses extra indices on this relation, on this approximate equivalence relation, to guarantee soundness. You can see our paper for details. The power of our equation logic is derived from its strong congruence rules. For example, if you know that P is indistinguishable from Q, then P composed with R is indistinguishable from Q composed with R. Congruence rules allow you to break your protocol into pieces and reason about each piece separately, which enables compositional proofs. I'll now give you a flavor of how equational proofs are done in IPDL. First, at the protocol level, we can perform an inlining step. We see that C is still defined locally, but only used in the body of O. In this case, we can actually inline C into O directly, which gets rid of C and instead has O do the sampling itself. Similar to other probabilistic settings, this inlining step is only sound if this channel C is used linearly. If it wasn't, then we would be duplicating this coin flip effect in an unsound way. Similar inlining rules also exist in IPDL for the nonlinear case, but this requires that the channel being inlined basically doesn't contain any probability. Now, we can perform some rewrites on this reaction for O itself, which again samples a coin flip, reads from this channel I, and outputs the XOR of the two. The first thing we do is we commute the first two lines to do the read first. Indeed, we have that reactions form a commutative monad, so all of the ordinary techniques for reasoning about monadic programs apply here too. After we commute the read over the sampling, we perform a probabilistic rewrite. Given Y, flipping a coin is the same thing as flipping a coin and then XORing with Y. This rewrite is sound since XORing with Y is a bijection and flip is uniform. IPDL is easily extendable with new probabilistic equivalence rules. At the IPDL level, they're considered axiomatic, but they can be proven sound using standard techniques. Finally, since XORing with Y twice results in all zeros, we can simplify this reaction to one which just reads from I and outputs the coin flip directly. Crucially, here we're stuck and cannot perform any more simplifications. For soundness, we cannot simplify away the read operation because we have a non-trivial logical timing dependency that's observable by the environment. Now let's turn to approximate reasoning. We model cryptographic hardness assumptions using approximate equivalences. As an example, we encode semantic security through encryption through this protocol, encreal, which first generates a key K internally, and then on input MJ, outputs the encryption of MJ under K. Here, J ranges from 0 to some number of queries Q, which is a parameter of the protocol. Parameterized protocols like this are not part of the core language of IPDL, but are instead encoded using metaprogramming. Using metaprogramming keeps the core theory of IPDL simple and gives us the flexibility to define protocols in terms of a wide variety of parameters, such as the number of queries or even inductively on Boolean circuits. Semantic security guarantees that this protocol enc_real is approximately equivalent to enc0, where enc0 encrypts zeros for the jth ciphertext instead. It's straightforward to see that this approximate equivalence is implied by the ordinary on-paper definition of semantic security for encryption. Thanks to the congruence properties of our approximate equivalence, it's easy to carry out entire crypto proofs using only IPDL's equational reasoning. Given a protocol P, which you want to prove is observational equivalent to some idealization, P ideal, you carry out a number of reduction steps. Each reduction step is an IPDL protocol context, here R, applied to a protocol which you want to replace, here enc_real. If you can prove that P is equal to this R applied to enc_real, then from congruence and the definition of security from before, you know that you can replace enc_real with enc0 inside of R. And then you can finish the proof by just iterating this reduction technique. Once you prove that P is secure, it's easy to then apply this result in bigger protocols via the same reduction technique. Now, for the soundness of our logic. Since IPDL protocols are in this restricted setting of networks of reactions, we do not want to define observational equivalence internally via contextual equivalence in the language. Instead, similar to crypto papers, protocols will induce a security game with an arbitrary polynomial time probabilistic adversary who may supply inputs, query for outputs, and eventually terminate with a decision bit. In turn, we prove that if IPDL says that P equals Q exactly, then for any adversary, the decision bit B needs to be equal in distribution in these two security games for P and Q. We prove this result under the hood using bisimulations, but this is a one-time proof effort. The end user only sees the equational logic. Similarly, we prove that our approximate judgment, which is actually formalized using families of IPDL protocols, Pn and Qn, where n here is what's called a cryptographic security parameter, guarantees that this decision B is negligibly close in distribution between the two sides. To apply IPDL to our case studies, we embed the core language and equational logic of IPDL into Coq using a shallow embedding. As mentioned earlier, realistic protocols involve parameters, such as this number of queries, Q. To write protocols that depend on parameters, we take advantage of the BigOp library from SSReflect. Since parallel composition in IPDL is associative and commutative for exact equivalence, we get a bunch of lemmas about parameterized protocols for free from this BigOp library. Now, to complete our case studies, we mechanize a bunch of semi-automated tactics and expressive lemmas for easy reasoning about protocols. For example, to prove that an index composition equals another one in a common context R, it suffices to prove a simpler lemma about each PI individually. Lemmas like these are proven by induction at the meta level in Coq. So while the core language of IPDL is extremely simple, our use of the higher order proof assistant Coq for the meta language allows us to recover enough explicitity for realistic protocols. Our case studies range from simple encryption protocols, such as a little secure channel example protocol that's just a few lines, all the way up to a full-scale secure multi-party computation protocol, GMW, as well as this randomness generation protocol, the n-party coin flip protocol, which is defined for any number of parties n. This GMW protocol is interesting because it's defined by induction over arbitrary Boolean circuits, and the proof, again, proceeds by induction on the circuit. While the n-party coin flip protocol is interesting because it supports a nearly arbitrary subset of fully corrupted malicious parties, which presents interesting complications for the proof. The high-level point, though, is that the proof size for all of these case studies is extremely small, with the largest one being only around 2,200 lines of code for the definitions and proofs combined in Coq. Also, we think that the proof experience often is much smoother than prior work. Our case study of observational equivalence for this one-time pad using Diffie-Hellman key exchange has been encoded twice before in the sequential proof assistant EasyCrypt. Once took over 18,000 lines of code for a first effort, and for another one it took over 2,000 lines of code. In contrast, ours takes only around 700. Both prior efforts also make use of complicated explicit bisimulation relations, while ours only makes use of simple equational rewrites. So to wrap up, we present a new core language for equational proofs of crypto protocols. This equational proof style is particularly good for cryptography, and it enables simple and compositional proofs, which allows us to perform a bunch of nice case studies in Coq. Please see our paper for additional details, such as our semantics and more details about our case studies. Our repository contains our code in our technical report, and my email address is given here. Thank you.
Questions?
Hi, I'm Faizan Asroli from CISPA in Germany. I'm wondering why LPDL doesn't have the replication process, because the replication is very important in the protocol and sometimes it causes the attack.
So we do encode replication, but because of the cryptographic domain, you assume that your protocols are always polynomial time. And what this means is that you encode replication by just metaprogramming away. So like bang p is like bang sub like number of replicas p, which then expands to just p composed with p many times.
Okay.
So we do at the meta level in Coq talk about replication, but the core theory does not have the replication in it.
Thanks.
Andy Pitts, University of Cambridge. So you mentioned soundness, but you didn't say anything about completeness. Can you say something about that?
Yeah, we haven't really addressed completeness very much. Partially because we are reasoning about like we are reasoning about concrete semantic operations like XOR and flip and these things, which we kind of axiomatize how they work in the Coq development. The completeness story for IPDL would likely talk about uninterpreted functions in some sense, and we didn't think that that was something that we wanted to get into. But I think that's definitely a good inspiration for future work.
So I guess a follow-up is, are there protocols that you know of that this technique is just either has trouble with, right? That this technique would not really be able to handle?
Yeah, that's right. So yes, there are definitely protocols where this happens. So the core inside of IPDL is this confluence property, which is given by the networks. And another way to think about this confluence property is that internal to the language, you cannot observe the non-presence of a message from somebody else. You can only produce more messages given input messages. But the thing is, like,
that congruence or confluence?
Confluence. I can discuss later why that's the case.
Okay.
But an example protocol where this happens is a protocol with timeouts, where you wait for X seconds, and if you don't get a message, do something. But we also have ways of kind of encoding timeout-like behaviors in the calculus.
Thanks.
Hello, I'm Jed Giuliani from the University of Cambridge. So I notice you guys are using a lot of diagrams and talking about, associative operations and fun stuff like that, which, screams a symmetric monoidal category to my corrupted mind. So have you guys considered such perspectives?
Perhaps. So I guess the commonality here is we really care about having good equational rules and foundational techniques for doing, axiomatic reasoning. And, if you think of this from proof theory or category theory, it's all kind of the same stuff. But we have not really taken like a categorical lens to this stuff yet.
Because it might allow, different rewriting strategies that take advantage of the parallel composition.
Hi, I'm Andrew Wagner from Northeastern. You mentioned UC in the beginning as the gold standard. Can you say a little bit more about the relationship between your network model and the sort of real UC model? What you think the relative strength of IPDL adversaries are with standard UC adversaries in particular? If a protocol is secure here, should it be secure in proper UC and vice versa?
Yes. So the first thing I'll say is that our soundness theorem given here applies to arbitrary polynomial time algorithms for the adversary. So you do not assume that the adversary is one of these networks. The other thing I'll say is that I like to think of UC as having two kind of orthogonal angles to it. The first angle is the definition of what's called the UC simulator in this environment and the way that you talk about what security means. And the other angle to UC is the kind of the semantics of it, given by interactive Turing machines. So like our insight is essentially we replace the semantics of UC with this like slightly restricted semantics for easier proofs. And we're currently looking in how to kind of lift the proofs done here back to UC, back to the classical interactive Turing machine model.
So I'm wondering, do you model the protocol from a specification or do you extract it from the implementation?
Oh, that's a good question. So this work, yes. So the question was about, are the protocols coming from some kind of abstract definition or are they being extracted by the implementation? And this work is only about modeling the high-level cryptographic protocol design as seen like on paper. So there's nothing about implementations really yet in this work. So like the way that we do the modeling here is we like look at the on-paper definition of the cryptography and we write down the model from this informal definition.
Let's make this the last question.
So one important component of UC is the import mechanism.
when you are doing equational reasoning, do you account for import in IPDL?
The import mechanism?
Yeah, import is like you want to establish this polynomial time constraints that you're talking about. You exchange import between ITMs, and then the runtime of an ITM has to be polynomial in the import.
I see. Yeah. So that mechanism to me is something that is there because you want to enforce that the protocol is polynomial time to ensure simulatability. But the reason you need it in the UC framework is because your protocols there are extremely general and can do arbitrary loops. But the core calculus of IPDL is terminating. And because of this, you can do much simpler techniques that are described in the paper to guarantee polynomial time.
All right, we should stop there. Thank you so much.